When we've talked about failure modes, you might recall that we said a thing fails when it no longer functions as intended. Doesn't necessarily mean it broke in two, it just no longer functions as intended. And when we're thinking about beams and columns, there are three primary ways beams and columns could fail. There could be an elastic failure, so it deforms too much or deflects too much, but it's still within the elastic limit, so it will spring back when you take off the load. Or maybe it will yield. It will go beyond the yield point and go into the plastic failure, the old silly putty where it starts stretching. A third way that beams and columns can fail, especially columns, is by buckling, and that's what we're going to look at today. Buckling is where a thing suddenly has a large deformation with a not very big load increase. And maybe you've experienced this if you had something like a steel rule and you press down on the top of it, and I don't know if you've had this experience, it just kind of sits there and doesn't do anything until all of a sudden, with unexpectedly boing, it boings out. That is buckling. Maybe you've had that happen with something like, an aluminum tent pole, where you're trying to put a tent up and all of a sudden it just sort of bends in half. This is a problem in buildings. So this sudden large deformation with only a slight increase in load. And usually when that happens, you have not reached the yield stress yet, but because things are just a teeny tiny bit off center, buckling will happen. And it happens with things that are long and slender. Let's pause for a moment and think about what is the difference between a beam and a column. If you ask many people, what is a beam? They will probably say, oh, it's a thing that's horizontal. But actually, that's not the whole story. A beam is something where the load is transverse. That is, the load is more or less perpendicular to the axis of the beam. It doesn't have to be 90 degrees, but in that general zone, it's not parallel. And a beam carries loads by bending. You have a support at each end, a load in the middle, and the beam bends. You're familiar with that now. It could be a ladder against the side of a building. That could be a beam, even though it's not horizontal. If the load is more or less transverse, it acts as a beam. A column, on the other hand, has loads that are parallel to the axis. In other words, they are axial loads. They're parallel to the axis. And a column carries its loads in compression. There's a load at each end, squeezing on each end parallel to the axis, and the column compresses. So beams have loads that are transverse, and they carry their loads by bending. Columns have loads that are axial or parallel, and they carry loads in compression. And as you can see in this diagram at the bottom, you could have two different members sitting at the same angle, and yet one could be a beam and the other could be a column because of the way the loads are being carried. Today we're thinking about columns. So how can columns fail? Well, columns could fail just in compression. If you have a short, thick column, a post under a house or something, and the load is too heavy for it, it will fail in compression. It'll just kind of squish. If you have a long, slender column, however, it will fail by buckling, that sudden deformation with only a slight increase in load. And by the way, the other day, a few days back, we talked about Greek temples made of marble, and the columns in Greek temples never failed in buckling, because their thickness relative to their length made them more of a short, thick column. So they were never long and slender. They never buckled. If you want to resist buckling, the very best shape is a tube or a pipe. And think back what you know about moment of inertia. Why that's so good is you are getting material out away from the bending axis. So a round pipe is the very best, but columns in buildings often use wide flanges because they're easier to attach to, and wide flanges are pretty good, pretty able to resist buckling also. What we know is that the more long and slender a column is, the easier it is for it to buckle. The smaller the load it will take to cause it to buckle. That critical load that will cause the column to buckle depends on how long and slender is the column, what material is it made of. So a rubber column will buckle sooner than a steel column. And how is it supported? So is it pinned at each end? Is it fixed in concrete at each end? And so forth. We'll look at that next time. So when you're designing a column, the first thing you want to ask is, could it fail by buckling? If you've got a short, thick column, the answer is probably no. So to answer this question, will it fail by buckling, you look at something called the slenderness ratio. And if it could fail by buckling, then the next thing you look at is how big a load will it take for it to buckle. And that load is called the critical buckling load. The critical load that would cause that long skinny thing to buckle. To analyze whether the column will fail in buckling, to analyze the slenderness ratio, you look for a number. And if you are looking at a wood column, like the picture on the right, you look at the thinnest width, we call that D, the thinnest width D, and the length of the thing, the length in inches. So length divided by skinny thing, skinny width. And for a wood column, if that number is greater than 80, it will fail by buckling, given enough load. If you have a steel column, the slenderness ratio uses the length divided by a property called radius of gyration, which is another shape factor. We're not going to talk about radius of gyration this term because we're kind of running out of time, but it's like section modulus and moment of inertia. It's a shape factor, and we can look it up. And so with a steel column, if length divided by radius of gyration is greater than 140, it can fail by buckling. So here we are in a table. With a wood column, the slenderness ratio is length divided by shortest width. And if that ratio is greater than 80, it will buckle. For steel, the slenderness ratio is length divided by radius of gyration. And if that number is greater than 140, it will fail by buckling. And I added a note at the bottom, be sure to convert feet to inches before you do this. I stuck in this slide, in case you're interested, here's what radius of gyration is. Don't worry about it. If you're interested, look at this. If you're not interested, we'll move on. So there's a small thickness and a wider thickness, and the column, if it's going to buckle, will always buckle in the thinnest direction because that's where it's the least stiff. So that's the direction that we'll look at. And we will first look at the slenderness ratio. How slender is it? Can it fail by buckling? And if it can, then we will go on to look at how big a load is the critical buckling load that will make it buckle. And here are two different flavors of the formula for critical buckling load, or P crit for short. Remember, P is force or load. So P crit is the critical buckling load. If the column is long and slender enough so that you know it will fail by buckling, then this is the critical load at which it will happen. Now, notice that both of these versions of the formula, and you can pick either one you like, both of them have a modulus of elasticity in the top, so it depends on how stiff the material is. And both of them have stuff that relates to stiffness of the shape, and both of them have a length squared in the bottom. What that means is that this critical buckling load is really sensitive to how long is the column. If your column were to double in length, the critical buckling load would be 1/4 as big. If you cut the length of the column in half, the critical buckling load would be 4 times as big before it would cause a problem. So length is really an issue, and then the shape, the moment of inertia, or its cousin, the radius of gyration. To summarize, first you look at the slenderness ratio. Will it fail by buckling? It will fail by buckling in a wood column if the slenderness ratio, length divided by thinnest width, is greater than 80. And in a steel column, it will fail by buckling if the slenderness ratio, length divided by radius of gyration, is greater than 140. And we'll practice with that in the next set of slides. So once you find out, yes, it's slender enough that it could fail by buckling, then step 2 is to go on to the critical buckling load and find out how big a load will cause that buckling. And you have two different versions of the formula. You may pick whichever one you prefer, it really doesn't matter, to figure out how big is the load that will cause this slender column to buckle. Now in the next set of slides we'll practice with this.